Thank you all for coming. So we're moving on with the next bit of the event. We'll have a panel discussion now. Um, we're not actually running in a webinar format, so we'll run in the following way. Can the panelists I'll be asking questions, and then if the panelists can like sort of take turns answering by raising a hand, and then you can answer, so we don't like interfering with each other saying stuff. And so it's a little bit more orderly. So without further ado, I'll introduce our panelists. So you've already met Rowan, and you've seen sort of Thomas around. Thomas Dietrich is a professor at Oregon State University. He's worked on many different things, including robust machine learning, on out-of-domain detection and anomaly detection, and he's sort of had a very long and distinguished career in machine learning. So let's welcome him. Next, we're having Ramon Ostadillo, who is currently a researcher at IBM. Prior to this, he's worked on many things. He's worked on Babel. He's worked on things like uncertainty estimation, uncertainty propagation, and speech. And currently, he works on semantic segmentation, semantic parsing in NLP. And finally, we have Professor Sergey Levin from UC Berkeley, who's worked on, again, very many different things, including robotics, reinforcement learning, again, the robustness to distributional shift. He's had a hand in like releasing the Wilds dataset, which was mentioned by Kate Saenko in the previous talk. So yeah, so let's welcome them all, and let's get started. So yeah, I think we're all good. We're all recording. If anybody in the audience has like any questions, you just write in the chat, and we'll sort of handle them as they come, and maybe I'll ask that question as well. So first, first question. Let's get started with that. So, in what ways does distributional shift show itself in the applications you work on, and what risks does it pose? Do you have any examples where distributional shift has significantly impacted your models in interesting ways?
I could start.
Sure, go.
So I can give kind of a dry technical answer, and then maybe an entertaining anecdote to compensate for the dry technical answer. The dry technical answer is the following: that in controls, in reinforcement learning, imitation learning, other kind of learning-based control areas, distributional shift is a really big deal, not just because you might encounter unfamiliar situations because of the usual reasons that we worry about in computer vision and so forth, but also because choosing your own course of action induces distributional shift even when you're in a familiar environment. So in some sense, if we're dealing with passive perception, if we're dealing with vision, NLP, et cetera, distributional shift is something that kind of happens to us when we step outside of the standard IID problem formulation. In control, it always happens. Like the exception is when it doesn't happen. So in that sense, we need good methodology to figure out how to deal with it. Oftentimes in reinforcement learning, you deal with it by doing online updates essentially, but that's not always practical. So that's something that I worry about a lot. In terms of examples, to compensate for the slightly dry technical answer, I can give you a little. I can give all of you a little example of something that kind of messed me up a little bit in a project that I was doing a few years ago. So some of you might have heard about the arm farm project at Google, where we set up a large number of robotic arms and we tried to have them learn grasping behavior. So they were picking up objects and training on large numbers of objects to figure out general purpose grasping. And one problem that I had is in my test set, I had a test set of objects. There was a pink stapler, and for some reason the robot would always mess up on the pink stapler. And I realized after a while that what had happened is that during training we had some cloth objects, some clothes, and because the robot gripper is kind of small, we had small items of clothing. They were usually baby clothing, and baby clothing tends to be in pastel colors, pink, light blue, that sort of thing. And the association that the system picked up on is that pink items are ones that are soft and made of cloth, and therefore should be pinched in a very particular way, which really doesn't work for a pink stapler. So this is an instance of something where there is actually, this is exactly distributional shift. It's distributional shift because there's a correlation at training time, which is pink equals soft, that is not present at test time. And it's a realistic thing. Like this kind of stuff actually would probably mess up, like, you know, a robot grasping items in the Amazon warehouse, because there would be baby clothes and things like that.
Yeah, so this actually like really reminds me of things that happens, for example, in translation models when you sort of decode, and they can also go off rails. So I think in many autoregressive scenarios, this is actually quite true. Yeah,
so I can talk a bit about two of my domains. So my first case, it was you know, several years ago, I was working on using computer vision to try to recognize insect species as part of a EPA project on assessing the health of freshwater streams in the United States. So it turns out the insects that live in streams are used as bioindicators of the level of pollution in the stream. And my collaborators went out and collected 100 different specimens of each of the 54 species that we needed to recognize. And we built a computer vision system for this. This was in the pre-deep learning days. And it worked pretty well, but then they didn't point out that when we would get real field samples from these streams, there would be all kinds of other stuff in them. So it was a open category or open set problem that at test time, there you know, something like 1,600 species of insects, and we had only learned 54 of them for our problem. So and so the system turned out really not to be usable because our equal error rate was 20% or something, and that was just too horrible to deal with. And then the other thing is I've been working more recently on weather data, which really is what caught my eye about this workshop today. And there, I'm part of a project called TAMO that is operating a network of automated weather stations in Africa. And so we have about 650 stations now. These stations, you know, have 6 or 7 different sensors on them. And they work fine in the lab, but for some reason we want to stick them out and have them experience the weather. And so then they get dirty and they break in various ways. And so there, the distributional shift is, I guess in one sense, is that the sensors themselves break. But the other problem is that weather as a time series is very irregular. And so detecting that the sensors are broken really requires us to have some expectation for what they were supposed to be reading, which means we need to predict the weather. And as people have found out in the weather challenge here, weather data is just really, really chaotic and difficult, full of trends and cycles and short-term departures from those. And so that's been, I still would say we don't have a fully satisfactory solution there. Our main strategy is to try to have weather stations close enough together that we can use them to check against each other. So, and since they're more or less experiencing the same perturbations and chaotic behavior, this is the closest we've come. We haven't been able to model and detrend the time series itself, but maybe we can borrow some of the ideas from the challenge here to address that.
So just to complement what has been said here, like I think what I can say, given my experience, I can paint a positive picture from my personal perspective, right? I used to do speech enhancement, so integration of modules that remove the noise from speech and interface with transcription systems like automatic speech recognition. That was my PhD and postdoc. And then I did machine translation. I was leading the quality estimation team for Unbubble, which is a Y Combinator startup, where you can imagine like having been able to detect that the translation is not correct was of capital importance. Actually, like what we had is a system that basically decided either to forward the translation that the machine did directly to the client or pass it to a human for correction, right? So this was kind of a very critical thing. And then lately I'm leading a team in semantic parsing at IBM. It's more focused around semantic parsing, but we also face the problem of real world outputs, right? And parsing is a very fancy thing that it used to be quite delicate. And I think as a general picture, I would say from my experience in speech at the beginning and now, it has improved incredibly, like really, really good, right? Like even if shift still is a problem, I have to say that at least the kind of problems that we have are fundamentally different. The same goes with machine translation, but probably still is not there. And now, for example, for parsing, that we're working with these pre-trained transformer models, they really are at another level when it comes to resisting this kind of distribution shift problems, right? But if I were to bring an anecdote, as you can imagine, machine translation is the more delicate of all. And we had a number of cases which are very funny if they happen when you're preparing a paper, but they're not funny when your team is basically on a trial with an important client, right? So these usual things like, I cannot basically give too much details of which company was involved, but they gave us some translation problem, but include code verbatim, right? And the machine just went completely bonkers. This was like 3 years ago. Like we were starting to get to know the neural machine translation systems. And from time to time, these small distribution shifts, they will balloon into completely crazy errors, right? It's not that the model kind of reduces its accuracy or its performance, it would just completely collapse. And collapsing in a product is really bad, right? And it would end up getting like a real phone call from a client, which is not good. So yeah, to summarize, I think it has improved incredibly. I having been an ASR guy for many years, nowadays, I wouldn't believe that it would come to this point where I feel like it's really working to a point, right? But at the same time, we still have a lot of things to do, right? And I'm surprised to the extent to which even companies, for example, that have products, they don't care enough about these kind of things, right? I think there should be more effort directed into this kind of problems, particularly because there's a lot of money on the line, right, when you do these things. Yeah, but that's basically it.
From the TRI side, I think, unfortunately, because of COVID, I haven't been able to see a lot of the machines yet to find a lot of like fun stories like everyone else has been able to share here. But I think like a lot of the kind of distributional shifts that are kind of obvious is like through different, through like spatially different geographies will have different rules and stuff like that. But then also through time, like it's kind of interesting with like all of these new types of mobility that are on the roads every day, like with electric bicycles and then electric skateboards and electric scooters and stuff like that. Like I think in autonomous driving, we often like to classify a discrete set of the types of mobility that are on the road for classification purposes and then, you know, prediction purposes. And like the fact that this is kind of like changing from under our feet all the time creates challenges. But yeah, hopefully next year I'll be able to have some more fun stories on exactly how.
Actually, can I ask a follow-up question to Rowan? Would it be possible to, I don't know, monitor some websites or product reviews or something and find out that these new kinds of things are coming on the market, and then transfer, I don't know, recognizers from the Amazon catalog or something to the vehicle? It seems like there should be intelligence that the things are happening.
Yeah, it's an interesting question. The question is that easier, or is it easier to kind of do manually, or is it safer to do it manually? And just kind of update our data sets and go back to them and relabel everything again. And I honestly don't know the answer. One of the things we had thought about was, could we come up with latent variable expressions for what the class uncertainty is for a particular object that lives in a continuous space, such that if you see an electric bicycle, maybe the latent can find a description for how it's been moving in the past and kind of what it looks like that's somewhere in between a bicycle and a motorbike. So even though it's never seen it before, it's seen things that are similar to it. And as long as it can find latent states that describe the motion in the past, that may give better predictive power for the future, which is what we want for safe driving. But yeah, I will forward your question to our team to see if they have any thoughts on that. Thank you.
Right. So I think the next question really is like, are you using any like explicit approaches for improving robustness or for uncertainty estimation? And if so, what is the form of these approaches? If you're actually legally allowed to say.
Well, this is maybe not the most exciting answer, but for all of the RL and imitation stuff where this has come up, the go-to reliable and tried and true approach, which actually the least interesting one, which is to just collect more data. I mean, it's obviously easier to do that in a reinforcement learning setting because the data is self-supervised by the reward function. But just as another anecdote of this of how well this works, we used to have a lot of problems with the robots at Google, where initially they were set up in one particular room with artificial lighting. So if someone like opens the blackout curtains, now there's a big ray of light that falls in the middle of the room. Everything gets messed up. Okay, fine. We keep running it. Next time someone opens the window, it gets a little bit messed up, but then it corrects within a day or so. Then we move it to a different building. It gets messed up, doesn't work for 2 weeks. Then we move it to another building. It gets messed up and doesn't work for 2 days. And then most recently, about a month ago, we move it to a new building yet again, and it starts working within 4 hours. So I think that the lesson from this for me is that, okay, we can think of clever algorithmic ideas to mitigate distributional shift, induce invariance, etc., and that's very important to do. But being able to collect additional online data and adapt is a very, very effective way to deal with it. And the more you do it, the faster it becomes, because you have more breadth of prior experience to draw on. So, my opinion on this is that we should come up with clever algorithms, but perhaps one of the most effective things we could do is make it practical to apply that online fine-tuning kind of strategy as broadly as possible, because that's going to get us a lot of mileage.
Sticking to the same order of speakers. So I already mentioned with the weather data that we are basically engineering our way out of the problem by, instead of trying to treat each station by itself, using correlations among nearby stations, and taking advantage of our knowledge of the domain that weather signals are spatially correlated. So that's not a machine learning solution, I guess. That's a redefining the problem to try to make it self-normalizing. But for the open category, open set kinds of problems, I think while there have been lots of different algorithms explored, there was a nice paper out of Zisserman's group last month or the month before on Archive, basically arguing that if you just train a network with all of our latest, a supervised classifier with all of our latest tricks, with good augmentations, and train it for a long time, and use soft target, soft labels, that you can just use its max logit output as a very good uncertainty indicator, and it's competitive, at least on large data sets, competitive with all the other fancy things people have been developing. So it's another kind of example, kind of like Sergey's, is that the solution perhaps for a lot of this out of domain or open set thing is to really change our perspective from CFAR 10 and training on 6 classes and evaluating on 4, to imagine that we have done huge pre-training on tens of thousands of different objects under a huge variety of situations, possibly self-supervised, So we have extremely robust representations of objects now. And so now the chance that that we can acquire a new object in a sort of few-shot learning strategy, and the chance that a new object has a representation that is distinct from all the known objects in this learned space is much higher. And so coming back to Rowan's example, yeah, hopefully that latent space now, there's a place for that e-bike that's somewhere in the space. Ruslan Salakudinov had a paper on this a long time ago, where he had done self-supervised training on what at the time seemed like a huge number of images, 2 million images off the web. And he showed the ability to learn what a Segway was as a novel object, because you could tell it was a type of vehicle because it had handlebars like a bike. It had wheels that looked more like a motorbike. So he could correctly learn to recognize it from its parts. So he was also doing a compositional representation. So I think, maybe it reflects my classical AI background, but representation is the most important thing to do going forward.
I think there's a question for Sergey. Andre?
Yeah,
in the chat.
There was a question from the audience. So Vats was asking, if more data is the answer, do you look for some kind of active learning strategy to collect the most useful data, or how does it work in an online setting? That's a good question, actually. I was actually going to come to that.
I'm sorry, then maybe I do my part.
Yeah, I was actually going to explicitly pose the question about well, I guess the cat's out of the bag now. But is using just more data let's just ask the question: do we actually need algorithmic solutions, or do we just flood everything with more data? That's the question. In the area where we've got GPT-3 and all these other models were trained on insane and massive amounts of data, is more data really the best solution, or do we actually need, or do we still need algorithmic approaches as well?
Depends on how expensive the data is.
Yeah.
And if we're working on molecules or bacteria or some of these other things where there just isn't a lot of data off the web, or where you need, or where it's expensive to collect, then I think we need fancier things.
Yeah, and the fancier things might be also ways of generating data in a not straightforward way, right? Like not only collecting, but one thing that we have seen, having done speech, right? In speech, I was doing something that was neatly about uncertainty and algorithms, right? It was about modeling the uncertainty at the output of the module that cleans the speech and try to integrate that uncertainty into the speech transcriptor system, right? The automatic speech recognition. And that basically died when, not only when the deep neural networks came in, but also the scale. Once the scale of data sets increased, that basically stopped being useful, right? And then now on the NLP, you see the same, these very strong models trained with a lot of data. Data works better than anything else, right? But there's space to do something that's less boring than just label more data, right? There is a lot of work in trying to find the best ways to generate synthetic data, generate these kind of schemes, and it seems to be a shift towards that, right? A shift towards trying to find ways to adapt or based on the way you create data. There was this very nice work where actually it's actually a guy that's working at Unbubble now, where they would, for example, they wanted to do adaptation to a domain with just one sentence or two for machine translation, right? And if you just do gradient descent on that, then it's going to just overfit terribly, not going to work. So the trick was to basically get that sentence and then find a bunch of related sentences in your training corpus and pad yourself some sort of learning batch, right? And then adapt on that. And that worked pretty well for kind of compensating a change in domain that's very immediate, right? So there's the space also for fanciness. It's not completely straightforward, right? To say that yes, using more data. There's many ways of trying to do it in that way. What seems clear, at least for me, I'm a bit pessimistic on like I saw my PhD topic became completely irrelevant if it was very relevant before, right? And I was very much banking on feature side, like a feature enhancement, model, like feature-based enhancement. That all basically went down the drain. So I learned my lesson, and now I'm definitely data first.
One thing I might add about this is also that I think there's actually a big difference between the principle of add more data to make the model more generalizable or more robust at training time versus add more data to fix mistakes as those mistakes arise. And I think the kinds of methods for approaching those two principles are going to look very different. So it's like, you know, if we talk about large language models or things like that, or large computer vision models, you know, they generalize broadly because, you know, people put in a lot of work to find and put together very broad and generalizable data sets. But you know, the world is really big. So for any system that gets deployed in the real world, it is probably unreasonable to hope that it will not ever get messed up. You know, it was like Rowan said, like, you know, even if your model works great now, tomorrow someone's going to make a bicycle that looks half like a Segway and half like a, you know, a dinosaur or something. And there's no way that anything you've seen before could possibly prepare you for that. So you will make mistakes. And then the question is just how quickly do you fix them? Now, you could still fix them by collecting more data, but that's where actually a lot of potentially interesting research questions do come up. And that question that Vatsal Raina asked in the chat, I think gets at some of those, like, well, if you're in a safety critical setting, like Rowan's setting, maybe you collect some data online, but you have to collect it and use it fast enough so you don't hurt somebody before you've managed to adapt to the new situation, right? So there's like actually really interesting technical questions that start to come up there, and maybe we're not exploring those enough.
Yeah, I think it's always like it's always a common and interesting question. I think I mean I agree with a lot of what's been said here, and you know it depends on the domain. I think you know, with the domain that I'm more familiar with, autonomous driving, I think it is I actually, I mean, a lot of yeah, I mean, there is a lot of companies collecting a lot of data on how humans are driving cars, you know, especially companies that own the vehicles, that sell the vehicles. So like, you know, like Tesla and other groups that, you know, they can collect a lot of data, but I still tend to think of it as like a small data kind of regime, because the world is just so complex that, you know, even if you have 100,000 hours of data collection or whatever, there's so many weird things that can happen in reality. So I guess that's more the generalization angle, but yeah, I mean, like the angle that Sergey mentions in terms of adaptation, like, you know, what do you do if it's your first time driving on snow? Like, humans are generally pretty good at figuring out, like, hey, you know, the coefficient of friction is different to the past 20 years of my driving. And whatever this data is that I'm collecting in the last, you know, 20 seconds is now like way more important than the past 1,000 hours of my driving. Or you know, or even things like, you know, going to Europe and discovering roundabouts and like, you know, oh my gosh, I haven't seen this before, but like, oh, you know, there's a car ahead of me and I can see how they're taking this turn, and off this 10 seconds of data, I'll try to figure out what it is that they were doing and what the, you know, the intention of the intersection is, and then completely adapt to the last 10 seconds of data that I've seen. I think, and I forget if it was who it was that, but you know, in terms of cost and things like that, you know, often recording people driving can be quite cheap. But there's other interesting areas where data can be very expensive. And you know, so one of the things that we're often interested in is dual control between the machine and the human, especially if they didn't see something or a deer jumps out on the road and they didn't quite react. Collecting that kind of data on like where both the human and the machine are either vying for control or both in control at the same time, that's much more expensive data to acquire. And so maybe, you know, maybe we don't have the resources to collect, you know, hundreds of thousands of hours of that kind of data. And then we need to think more about our models and our inductive priors and what kind of, you know, how to better extract knowledge from small data sets. Yeah.
Right. So that's all quite very interesting. So I just had maybe a side comment, even though I really shouldn't try to interfere, although it's so interesting to actually try to participate. But anyways, about things like causal inference. So Judea Pearl has this claim that like you can't actually learn about causal relationships from data unless you posit a causal structure. Now, presumably, like you have models like GPT-3, which can, perform really cool gimmicks and be basically an amazing stochastic parrot. But if you actually try to ask it about some kind of why questions, which, where the model you should learn something, like understand something about some underlying structure of the world, like a causal structure of the world, then it might like really mess up. And it's unclear how you can overcome this by just collecting more data. So, like, do you have any thoughts on that one?
I don't know enough about causality, but I mean, I do language modeling, right? I'd say that the general idea that I understand from it's reasonable, but the model might fail for other reasons, right? I think that the reason why GPT-3 fails is not because it doesn't interiorize a causal structure. It just lacks a proper hard or defined state over long context, right? It doesn't have a world model. It's a model of language, not a model of the world. But I wouldn't say you need causality for that, right? You need a predictive model of the world, and these models are trained with text. If you were to train them, if you were to train a person talking while driving, I don't know, or maybe as it is tried now, right? Like with video and audio, then there might be a model that makes more sense as an internal representation, right? But I don't know if causality is really the problem there. And I also don't know enough about causality, to be honest. I find it very interesting, but I haven't been convinced yet.
I mean, I think that there's some degree of validity to this stuff, and I think it's fair to say that different training algorithms can make models more robust for answering counterfactual questions, which is a lot of what we actually want models to do. We want them to make decisions, and those decisions, to a degree, implicate some amount of counterfactual reasoning. At the same time, in real world settings, it's very, very difficult to have things that are actually interventions. Like even if you actually have an agent that is embodied and actively interacting with the world, it's hard to have interventions. And if you are collecting additional data and labeling in various ways, well, then it's next to impossible to have interventions. So my take on this is that it's kind of, it's good to be aware of the issues, but at the same time, I kind of suspect that the way, basically, we're not going to be able to come up with some magical method that makes models perfectly correct or perfectly causal, which is kind of almost synonymous with perfectly correct. And therefore, we're going to need to deal with these issues no matter what. So while there's some progress that can be made with trying to set up training methods that don't constantly fall prey to spurious correlations, in the end, there's not going to be some like causal magic silver bullet that just like fixes everything. Basically, it's more useful as a tool, as a framework for thinking about the problem than as just like a magical path to a solution.
So, Ron, you want to go next? Sorry.
No, you go.
Okay.
You go.
Yeah, I mean, I'm a big fan of causal modeling. I've been doing a very small amount of it myself, though, so I can't really speak with authority. But my students and I had a paper at ICML 2018 on trying to detect and remove exogenous variables from an MDP. So, you can, I'm surprised Sergey says you can't have interventions, because in RL, you're taking actions which are intervening. Maybe the issue is it's not always clear which variables you're intervening on. And I think that is again, a representational issue. In Pearl's discussion, the variables are as well defined. But in the kinds of problems we work on, say in language or vision, we're not observing the variables. We're observing, sense data, human behavior data. But I was working on a problem in cell tower optimization for Huawei, and there your reward function is affected both by the variables you can affect in the world, but also by the behavior of all the users of the cellular system. And that made it hard for policy optimization to happen, because you try intervening on your variables, but the reward signal would be diluted by all this other variance coming from exogenous variables. So if you can basically do a little causal structural discovery and figure out which parts of the world do you affect and which parts do you not affect, then you can remove that exogenous effect, reduce the variance, and learn faster. So I wonder, even in language, like maybe in dialogue, again, there's an opportunity perhaps to figure some of those things out. Although I don't know, there's so many latent variables in dialogue. I think that's a huge challenge. Anyway, so I'm I don't know, moderately optimistic. It will depend a lot on the domain. When we're in medicine, reasoning about causality seems to be super important. But we also bring a lot of domain knowledge to bear. And in less well-defined tasks, I think in vision, again, we really would like to understand what parts of the image signal are caused by the object we're trying to identify, and what parts are these irrelevant bits. And if we have video, we can often figure that out. So it's not an interventional thing, but in some sense, the animate objects in the image are themselves intervening on the world, and that gives us a nice signal. So I think it's an important representational tool to bring into our toolkit.
Yeah, it's definitely an area that we're kind of very interested in, but I don't know that much myself yet. But the thing I was, and it was betraying my ignorance a bit, but the thing I was always a little bit unsure about with causality and time series modeling. So if it ever comes down to predictional planning, so for autonomous vehicles or other things, it's like, we still know the past causes the future. And so there is at least that we've got. Things don't happen. There's usually some kind of time delay between a cause and an effect that we can latch onto. But then I guess maybe one of the kind of questions in terms of that we still need to grapple with, especially with large sensors like LiDAR and vision, is how do you come up with a state representation that is Markov, that does summarize everything you need to be able to predict the future. So part of, I think possibly our only recent work on this was work with Sergey on biosimulation. So can we use state aggregation, and can we try to figure out the simplest MDP that we know of that doesn't sacrifice any information that is predictive of future reward sequences in at least, and there's a little bit of causal theory that goes with this paper, but basically to at least suppress sources of, additional signals, spurious correlations and so forth, to hopefully desensitize whatever downstream planner has to, any kind of additional signals in the environment that are probably irrelevant.
Right, I guess we can then move on to the next bit, which is really the previous bit, which I didn't ask. But anyways, so our current methods for improving robustness, or our current algorithmic methods for improving robustness and uncertainty estimation, sufficient for actual application to real-world tasks, or are they insufficient in some way? What are the properties? Like, what would be the desirable properties of a method to be applicable to real tasks?
I guess in the area of open set, I don't think we have any theoretical basis for giving any kind of guarantee. that we can detect novel objects. We have methods that work experimentally. We have techniques for trying to improve these sort of experimental measures, but I don't think we have a theory, say, of deep learning and deep learning representations in computer vision, for example, that would allow us to say anything formal. And that's because computer vision machine learning has been in such a empirical phase right now that we've been able to just add data and get better performance. And so far this seems to also be true of our, let's say, open set or anomaly detection methods too. So so I think we need more theory that would relate our, the sample size required for and the architectural properties of our algorithms and so on, that would be required to guarantee that we're learning models with a certain degree of accuracy. And I can't even articulate that very well, but so much of our work is based on hope and experiment, and not based on some underlying theoretical reason why the methods should even be working.
One issue that we often run into in robotics is that if you have a domain that is not a safety critical domain, well, I think it's fair to say, for example, that robotic grasping is not really a safety critical domain, and that you can mess up and you can try again. Then the issues exist, but they kind of don't matter as much, and we're maybe not so worried about uncertainty estimation, because as long as nothing broke and nobody got hurt, it's all okay. And then in domains that are safety critical, it's kind of the opposite problem, that, well, yeah, you want uncertainty estimation, but at the same time, the reason you want uncertainty estimation is because you want something that is bulletproof. So if your uncertainty estimation is not bulletproof, you're in some sense no better off than you start. Like if you have half the number of catastrophic failures, well, that means you still killed someone. It's just you did it half the time. So this is kind of the problem that I think a lot of, when the rubber meets the road, sometimes quite literally, this is the issue that uncertainty estimation methods run up against, is that you don't need them if you don't need to be safety critical, and if you do need to be safety critical, then the bar is so high. So for me, this is actually part of why I'm so optimistic about adaptive approaches, because I think that that's maybe one way that you could get something that is a little closer to bulletproof. But this is like just a really big conceptual challenge for real world applications of this stuff.
Yeah, I mean, definitely. I run a quality estimation in machine translation team that was basically doing something like that, in a sense, right? Like we were the ones that had to say this is okay, and it can be sent to the client directly. So that's a huge responsibility, right? So if you're going to do that, you have to be sure that you're not creating false expectations. And I think it's very easy people like these kind of magic boxes where they have a diagram and there's a box that says remove noise. And then they imagine that speech comes on one side and then it comes on the other side with absolutely zero noise, just completely matching your train set, right? And with quality estimation, it's the same. Like you would have these kind of arguments where somebody imagines this magic black box that says quality estimation, and now I have 100%, I know 100% of the time when the things are good or bad. And error propagation matters a lot in these cases, right? So yeah, I mean, I fully agree that you could be, as in Spanish you say, like rescuing a ship that's sinking with a plane that's falling from the sky. So you have to be sure that you're not basically adding more gasoline to the fire when you. So I think part of the resistance is that you have already enough problems. Maybe simpler the better. But there might be a method out there, right? That is for sure.
I think go ahead, Ron.
Oh, okay. Yeah, no, very quickly. I think, with different types of models and, epistemic uncertainty and aleatoric uncertainty. And I think one of the interesting things we think about with at least the stochastic forms of aleatoric uncertainty when it comes to driving in interactive scenarios is that, like, when training models using the negative log likelihood or something like that, it's often quite good at squashing down false negatives. And so that's very good for kind of predicting how other people will drive. And so, any kind of mode coverage behavior on like, not quite getting the uncertainty estimation correct, but if it's at least a little bit more conservative than what it arguably should be, that's not so bad when it comes to predicting how others, it's better to be a little bit more conservative or falsely conservative. The real challenge for us is actually when it comes to imitation. So there we really want to squash down not so much the false negatives, but the false positives. We never want to do something that a demonstrator never actually did, because there's probably a good reason why they didn't do that. And so that's a bit harder to optimize for, yeah, so that's at least the challenge in that domain.
And I was just going to make a minor remark that our representations of uncertainty require representations, right? We have a probability distribution over some space. And so if the space that is inadequate, then our uncertainty representation will be inadequate too. So for example, for open set problems, ensembles have not been very useful. They're great at capturing your uncertainty in the latent space you learned, but unfortunately the novel sets may all concentrate in some little point of your latent space and just be overlapping with known classes in some way. And so they pass undetected when you're doing uncertainty quantification. So that's what I think. I started out in open set and uncertainty, anomaly detection in standard feature-based machine learning. And there, everything was so easy because we always had a good distance measure and new things were always outliers compared to the training data. But once I moved into deep learning, we lost that because we're doing representation learning and we only really learn to represent the things that we've seen in the training data. And so that argues for either a lot more training data or creative augmentations or something to give us the ability to represent stuff beyond our training data. And this is the central problem of few-shot learning too, I think, right? That an awful lot of our few-shot learning paradigms don't really test how well we can represent things beyond our training data and learn them quickly too. So that's why I say it's all about representation.
Yeah, I think all that makes a lot of sense in terms of, yeah, like that we're still at the mercy of our models, and if our models suck, then obviously their uncertainties are going to also suck because they don't understand what's going on. Right. That moving on to the next bit. So we've talked a bit about like methods and either algorithmic or data driven about how to improve uncertainty, but how do we assess whether the models generalize well, whether the models are robust, and whether the models can actually estimate uncertainty in a meaningful way? Are current data sets sufficient for this? Or do we need new data sets? So actually, maybe I can ask that in a different question. So are current data sets sufficient? So data sets like MNIST, CIFAR 10, CIFAR 100 and such, is research on these data sets still meaningful, or do we need to move to something which is entirely different, removed from these data sets, maybe, more task specific across different modalities, different tasks and such?
I think this is actually a huge issue right now. So certainly for the way that we approach research on distributional shift, for example, for computer vision problems with corrupted versions of standardized data sets. I think that's actually really problematic. Maybe it's better in other domains, I'm not sure, but there's a fundamental challenge, and I have no idea how to deal with this, but the fundamental challenge is if you're constructing a benchmark for how your method handles distributional shift. Well, distributional shift is important when something like unfamiliar and weird happens. But by definition, a standard data set is not going to be unfamiliar and weird because it's standard. So there's just some very fundamental challenge there that makes designing a benchmark for distributional shift harder than designing a normal benchmark. Not to say that we shouldn't try, just that it's hard and we should think carefully about it. And second, I think at least for the, I can speak to the stuff that I've worked on, at least for the image stuff, and this was a big part of the motivation for us for Wilds, and I don't want to claim like I came up with anything. It was Pangwei is the one who basically, and Sherry were the ones who actually did everything. But and this was really their idea. But the motivation there was to come up with more realistic instances of distributional shift, because the current stuff was not very good. Rowan, maybe TRI should release, a benchmark of weird mobility devices on the street, like things that are a little more representative of actually how the issues these systems really face. Yeah.
We have the
because I think the corrupted stuff is, it has a purpose, but it's very limiting.
Yeah, strong agree from my perspective. I'm part of this DARPA funded thing called Sail On, and there is a red team that sets up the challenge, and we never see the data that they feed to our system. So they run our system and they evaluate. I mean, we are, I'd say, an issue is we don't really know what the right metrics are, but they evaluate our system's performance, and it's very hard for us to debug against that. So I think methodologically because there's like they are a black box. So it seems like we need somehow a pair of data sets, some data sets that we can develop and test our methods on ourselves, and then others where the novelty is sequestered from us and is behind some automated evaluation mechanism. And of course, eventually those will wear out too, but it avoids us knowing what the novelties are going to be and designing our methods to detect the ones that we know are there. Yeah, and so I do think that CFAR 10 is hardly useful for anything anymore, and CFAR 100 probably too. I think, unfortunately, I think we need to go to larger data sets. In this Zisserman paper that I mentioned, they propose, they have designed an ImageNet, a new ImageNet test set to combine with standard ImageNet to try to test. And they also have divided up the Cub 200 and the airplanes data sets to create interesting problems where they have measured the difficulty of different novelties so that you can have sort of easy, medium, and hard things to try to generalize to. But it will suffer from the problems that Sergey was mentioning, because we know what those data are. But if we behave ourselves as scientists and don't overfit to them, I think they will be useful. But that's why this workshop is so exciting, particularly because it seems to me that part of making progress is maybe trying to build, get some insight into the contextual cues for when to expect novelty. So when I get off a plane after flying across the ocean, I'm expecting that things will be different than they were when I was at home. And so I mean, that's sort of the simple case, but I also wonder if our systems, if various novelty detectors are kind of going off, isn't there some sort of a metacognitive level that's saying, gee, I think this world has changed in some ways. I should not be trusting my old models as much as I normally would, because just stuff, I'm getting little signals all over the place that things are a little different than they were in my training data, and somehow adjust our risk posture as a result.
It sounds like a generative model running on your head, like some sort of.
Yeah, I got a common filter, but the observations are over anomaly scores of various things, unfamiliarity scores or something. How many surprises have I had in the last 5 minutes that suggest that maybe this vehicle isn't working the way my dynamical model predicted, or I don't know. Yeah.
Yeah, probably your budget for surprises in automatic driving is pretty low, but in general, yeah. So I wanted to say I fully agree with what you just said about the data, right? And there's this sort of kind of absurd thing, which is you create a corpus about domain shift, right? But once people see it and once people start running experiments on it, right? One of the problems you have is that at the end, domain shift in a sense can be a problem of overfitting, right? Like if you have some data and then you have some data that's shifted, there is a degree to which that is shifted in a sense, right? Yes, making it very one-dimensional. And that means that people can kind of assess with very easy hyperparameter tuning to what extent, if it's a closed set, right? So the problem with domain shift is as well that how you create data, right? Every time you look at the test set, your corpus dies a little, right? And this happens in general with every corpus, and it's amazing how long do we insist in keeping corpora that actually, in my opinion, they're fully dead many years ago, and we still keep them because they have this kind of aura of things, right? But nobody cares. I mean, they're probably completely overfitted. For domain shift is even worse, right? Like imagine, because once you do like 100 tries, you kind of know, to what extent this relates to the corpora that I have for training or that I know. So it's definitely data in this case is even more complicated than for the normal case.
And yet people still publish on MNIST.
Yeah, I mean.
But we no longer consider it a computer vision data set, a database.
It graduated to a machine learning data set.
Oh, yes.
Maybe the test set needs to keep shifting so that people can't overfit.
I think Jan claims he has another test set that he's had never revealed.
Is there a hope with gigantic real test sets, not synthetic ones, but like if test sets were 10 times larger? It would be a pain to test, but I mean, that might help even.
But maybe what we should do is divide them up into, maybe we should divide those big test sets up into a series of them, and every year a new one is brought online, and any method that fails on that is just retracted from publication.
I mean, in some ways, in all seriousness, that is a kind of the lesson from ImageNet for me is that, well, something being big enough does make it kind of more resilient to, bad behavior on the part of researchers. So maybe, in all truth, that a partitioned, very, very large test set could overcome these issues just because it would be so large that nobody could, hack things together that work only on that. I don't think that's out of the question. I think that's very realistic, actually.
It is, yeah. I mean, just to reiterate what you, Sergey, and you, Thomas, have said before, I think it is a very important problem for us. This question on how do you test it? But how do you test it realistically to avoid fooling ourselves that we think we've solved something with a didactic case, but then lo and behold, in the real world, real world distribution shifts can look very different from what we think they might look like. So, I don't know the answer, but I'd love to know.
Yeah. So, and I'd just like to add that, like, a large inspiration so this is also like a thing I've been thinking about a lot. And I think that we're really motivated by like wilds to actually make shifts and collect all the data. And so it's still like up to like I guess we'll see how like resilient shifts will be to the and whether it will stand the test of time and whether it actually be useful for research. But so hopefully that may to some degree alleviate the problem. But I think everyone's really right that like we need continuously evolving test sets with like either so that you can never really fully adapt to them and in order to be actually able to evaluate your methods. So I think it really brings us to the last question is so what's next? What's the next frontier for uncertainty and robustness research? Do we examine more data sets? Do we examine data collection pipelines, adaptation, maybe uncertainty propagation? Like, what is it?
I really liked Rowan's talk today. I thought that pointed the way because it was looking, well, and to some extent, I guess the natural language talk too, was really looking at more of the systems issues. instead of just thinking about it as object classification or learning a dynamical model, we're asking, well, what is the real impact of errors or uncertainty in one component on the downstream components? And I think this is also, getting away from, we've been working lately on this human object interaction data. So a person riding a bicycle, where it might be a novel object, a novel verb or activity, or even a novel subject. And now you have really interesting composite problems of figuring out which things in the image are novel and which ones are not. So you just can't rely on a sort of global signal from your deep representation that says, well, it just looks unusual. And this is turning out to be quite challenging, because if you're using segmentation algorithms that give you bounding boxes, those bounding boxes are overlapping, and so it's easy to confuse novelty. If a person's riding a bicycle, is it the person that's novel or the bicycle that's novel, or both, when half of their pixels are shared? So I think that's just a baby version of the kind of problems Rowan was showing, where you have all these pedestrians you're trying to track and all these other objects, and some combination of them could be novel or be behaving in novel ways. And so I feel like maybe as we engage with more realistic real world problems, instead of these made up academic problems, that will be much healthier and greatly increase the probability that, I mean, as a field, we kind of have this, I don't know, sim to real transfer problem. Does the academic research transfer to the real world? And so partly maybe that is, let's make the task more realistic and therefore more complex.
I guess my response to the question, which I'll keep it brief because I feel like I've gone on at length about this already, is that I generally am of the opinion that while it's good to devise methods that improve robustness, ultimately, if we want things that are very reliable, we'll need methods that are adaptive, because I don't think we can make things that are robust enough such that they never fail, which means that the best we can do is get them to fix their mistakes as quickly as possible. So I'm pretty optimistic about research in that direction, and that's what my group is doing too.
Yeah, I mean, I work in language, so I might say something that's obvious for people that do, for example, reinforcement learning and things. But I have my hopes in, again, like trying the simple, boring things first, like more data, proper ways of simulating data. And I think parameterized simulators, like the entire world of models that learn how to generate data, it's a direction that has been growing in the last 10 years, but it's gaining strength and strength, right? And maybe for language particularly, it's unclear if it could happen that we found the barrier of language modeling, like language modeling without a world model cannot get much better than this, right? And maybe that's also a good thing in a sense. Like, for example, simulation opens the door to having much more sources of information, right? So I would say simulation is to me like kind of boring, but probably what's going to help make these language models and speech models more robust, right? And I mean, again, my PhD was in a very uncertainty propagation. I loved it. From the time they gave me the topic, I said, I love it. I'm going to do this, right? But the truth is, I mean, like they got run over by these models that just ingest a lot of data. So it might be that, yes, more data and simulation get us there.
And I think, yeah, my quick answer is, I think, yeah, what's next? I think, yeah, there's definitely more work to do in, representing scenes like Thomas was talking about. How do you represent something properly? And specifically kind of like, yeah, any kind of like high level relationships or abstractions you can pull out of a scene that are likely to hold true across different scenarios. So like if you can understand that a curb is never driven over no matter what its configuration, then when we see it in new configurations like the roundabout or some 45-degree turns or something like that, we can still understand that even though it's a new You know, it's a new, we haven't seen it in this shape before. We still understand what it means. It's something that delineates the edge of the road that we shouldn't drive over. And I think, you know, maybe it's a little bit, you know, boring for the deep learning crowds and stuff like that, and the end-to-end crowds. But like, I think inductive priors are really useful. I mean, it goes against the better lesson by, you know, Rich Sutton and so forth and colleagues. But I think, you know, the inductive priors, you know, if you have human knowledge, I think it, you know, especially in safety critical systems, I think it's always worthwhile using it. So any kind of knowledge of physical models or causal relationships that probably are likely to generalize into a lot more situations than the distribution of offline data that we may have. And, you know, and digging a little bit below the surface a bit to find some of the more fundamental reasons why people are making the decisions that they are. So, you know, anything to do with like, you know, inverse reinforcement learning, or like, you know, considering priors over, you know, where people are actually trying to aim at 30 seconds from now. All of that can really help to at least make, you know, prediction models that are, even if over the next 5 seconds, at least more consistent. And take into account more global information. Yeah.
Andre, I think there's a question on the chat for me, I think. I think somebody asked what I meant by simulation.
Yeah, so I think we can like take a couple of questions from the audience now before I sort of summarize what has been said here. So like the last question was about asking Ramon to elaborate what he meant about simulation.
Yeah, and I meant something like very naive, like imagine like some sort of program that generates a synthetic scenario that is very good, right? And in the case of language, you probably are opening the door to multimodality, right? You can have some sort of surrogate for what will be the other modalities. It doesn't have to be perfect image, but maybe some surrogate, and then you have that binded with text so that the model learns a predictive distribution over text and that other thing, right? I guess that the easiest thing is to think more of areas that I don't work with, like, you know, like reinforcement learning applied to real world audiovisual scenarios, right? Or you can imagine a video game or something like this. But in language, it might be also interesting, like to be able to produce text that's grounded on some sort of program that can provide you also with other modalities, right? And there's a bunch of work in this direction, but it's very simple right now.
Right. So there was another question from Dev Vidani on how do you foresee human common sense features abstraction handled for OOD data? For example, an unknown object hurling at high speed towards a robot, should it trigger ducking by a robot, or shouldn't the robot make determination of speed, perception of the weight of the object paper's rock before making the decision? Another example, previously unseen animal crossing the road versus a newspaper floating from right to left in front of a car. What should you do? What should you decide? If common sense feature set is an answer, is the feature set domain specific? Can you elaborate on what goes on in handling those scenarios for higher robustness versus failure trade-offs? Thank you.
Sorry, was that aimed at anyone, that question?
I think it was just like if anyone can take that question. It wasn't directed at anyone, I think.
I can try to take that question badly. I'm not sure if this is going to be a very satisfying answer, but you know, one thing I might say in regard to that is sort of a one man's common sense is another man's overfitting. Like, you know, on the one hand, it might be good to have a model that extrapolates that you know, a plastic bag floating across the road is not a dangerous obstacle. On the other hand, maybe you don't want that. So it's a bit situational. I do think that maybe this is part of what this question is getting at, is that one failure mode that current models sometimes have is not that they extrapolate in sensible but incorrect ways, but rather that they extrapolate in ways that are not sensible. So if there is a plastic bag floating across the road and it's never seen a plastic bag before, it's not that it will decide it's a different kind of obstacle, it'll just decide that it's something totally different. Like maybe it'll trigger a label saying there's a pedestrian on the side of the road instead. right? Because if it's out of distribution, any output could happen. There's no naively, there's no guarantee on anything like that. So I do think that it's worth thinking about methods that address that aspect of the issue, and I think that's what Tom was referring to as when he was talking about representations before, and how the representations kind of potentially go all into one point for some unseen stuff. But at the same time, it's still going to lead to mistakes, just different mistakes.
Yeah, I actually thought that was a pretty good answer. Right, so like we've gotten to the end of the panel, so thank you everybody for participating. I'll just quickly summarize that we've basically discussed like the nature of distributional shifts. We've covered a couple of examples. We've really discussed this concept of data versus algorithmic, and that like actually in many applications data just rules. You don't really need algorithmic, but in certain cases, human knowledge or maybe human structural priors may be actually very, very advantageous. The issue with uncertainty estimation is that if it's still model driven, it can still fail. So like it's not a silver bullet. In places where you don't need it, like which are not risk critical, you don't need it. Period. In places where it is risk critical, you need it to be at such a good level that may be unrealistic to have it. So yeah, then we've covered the datasets thing, and I think we can all unanimously agree that we need to bury MNIST, CIFAR10, and maybe even just only start at ImageNet, ImageNet C, R, A, and all those, and then move up from that to wild shifts and things like that, or maybe even new datasets and new evaluation paradigms with continuously evolving test sets, which feature realistic out of distribution, shifted examples. And such, so we've covered a couple of things on the frontiers. I think so. There's definitely one about uncertainty propagation through pipelines. Models don't live in a vacuum. Models exist in terms of complex pipelines, and that you really need to push through information from one part of the to evaluate how errors, mistakes, and uncertainty estimates from one component propagate downstream and how it affects the overall pipeline. And that actually is something I myself am thinking about, so I really agree with that point. We also had the point about simulation, and that we can try to collect data and try to just go for a more data-driven approach even further, collect data and try to go with these data-driven approaches. And finally, that also the whole adaptation approach, that you can instead of thinking in a static fashion about static data sets and extra data collection for static data sets, that we have this concept of continuous adaptation, where we can try to adapt to new data as it comes in, and then at some point that the last maybe 10 or 5 seconds can actually be more valuable than the last 10,000 years of data that you've seen. So I think all those are incredibly important, and I think so we had some really good points. So overall, thank you very much all for attending. Thank you all for being here and for listening. This really brings us to the end of the Zoom part. We'll be switching over for the rest of all this to GatherTown, where we have some more posters for everybody who wants to check out the posters or just hang out, chat, and discuss stuff. So that's all in Zoom. That's all in GatherTown. How to get to GatherTown, in case you've forgotten or haven't been there yet, it's via the link on the competition track, or I can just post a link in the chat. Copy link to everyone. Yes, so GatherTown is the next session, and I'll just to quickly say that so about shifts. So I've updated there's some comments about broken links. I fixed all the broken links. The full shifts dataset is now available on our GitHub, and you can download the full unpartitioned and also canonically partitioned versions of the dataset in all of the 3 tracks. So yeah, thank you again all for participating. Thank you all for your great keynotes and your amazing discussion. I think this has been really good, and it's far surpassed my expectations of what would happen. So thank you all very much.
Thanks, Andre, and thanks to all the organizers. It's such an important topic. I hope you consider doing it next year as well.
Yes, thank you.
Thank you very much.
This is actually we're definitely considering going for something next year, but we're trying to think of ways of making it actually interesting. Now, so it's not just a rehash.
Sounds great.